Welcome to The Explainer. Today, we're going to unpack one of the most deeply fascinating mysteries of our entire universe. We're talking about the invisible push and pull that dictates literally everything around us. I mean, it's happening right now, at this very second, between the atoms in the screen you're looking at and the atoms in your own eyes. It's incredible. We are diving into the precise mathematical laws that govern our physical reality, specifically focusing on the math behind point charges. Seriously, think about it for a second. What are these invisible forces pushing and pulling on you right now? And how do we actually calculate them? It's pure observable physics. You can think of mathematics as our ultimate decoder ring for understanding the fundamental forces holding our physical world together. Because honestly, without these very specific calculable forces, you, me, and the chair you're sitting in would all just dissolve into a chaotic cloud of atoms. No way we want that, right? So let's figure out how to make sense of this invisible architecture.
Okay, let's dive right into this. Section 1, meet the electric charges. Before we get into the heavy math equations, we really need to understand the fundamental building blocks of electrostatic forces. Now, when we want to measure exactly how much charge we're dealing with, we use a specific unit called the coulomb, represented by a capital C. And there are two distinct types of charge here, positive and negative. The golden rule for how they interact is pretty straightforward. Like charges are always going to repel each other, while opposite charges attract. It's this continuous, dynamic dance of pushing away and pulling close. But our source material highlights something else that's absolutely essential. Charge is a conserved and quantized property. That means charge can't be created or destroyed. It is strictly conserved. And it's quantized, which just means it only exists in distinct, discrete packets. Nature operates on a very precise accounting system, you know? You can't just have an arbitrary, random fraction of a base charge. It has to be exact.
So what happens when we introduce a second charge into the mix? That brings us to Section 2, Coulomb's law, the force equation.
We know from basic physics that charges will either attract or repel each other based on their signs. But to truly understand this interaction, we need to calculate exactly how much force is actually at play. Let's unpack Coulomb's famous equation together. F equals K times Q1 times Q2, all divided by R squared. It's a really logical recipe. F is the final force we're calculating between our 2-point charges. K is a constant, basically a fixed number that aligns our math with the actual physical universe. Next up, we have Q1 and Q2, and those represent the actual quantities of our two interacting electric charges measured in coulombs. Finally, R stands for the physical distance separating those two charges. So you just take the magnitudes of the charges, multiply them, apply that constant, and then divide by the square of the distance between them.
The crucial thing here is understanding what this math actually means in the real, physical world. The first big takeaway is that force increases with charge. Larger charges just give you proportionately stronger interactions. But pay close attention to this second principle. Force decreases as distance increases. Because that distance variable, the r, is squared in the denominator. Moving charges apart rapidly kills the force between them. It drops off incredibly fast. And this force acts directly along the straight line joining the two charges. Grasping this dynamic is absolutely essential because it drives all electrostatic attraction and repulsion, and it forms the entire foundation for how we calculate electric fields.
All right, let's get our hands dirty. Section 3, doing the math with point charges. It is time to plug in some real numbers.
Let's look at a specific calculation straight from our source material so we can see this equation actually tell a concrete story. We start with our constant k, which is 8.99. Then we multiply that by our two charges, Q1 and Q2. For this example, we've got a positive 3 coulombs charge and a negative 3 coulombs charge. Well, multiplying 3 by negative 3 gives us negative 9. Simple enough. We take that result and divide it by the distance between them, squared. Here, the distance r is 4 meters, so we divide by 4 squared, which is 16. So the whole setup is complete. 8.99 times negative 9 divided by 16. And boom, the result is negative 5.06 newtons. But what's really interesting here is that negative sign. It isn't just some mathematical quirk. It's telling us a profound physical story. A positive charge and a negative charge are going to physically attract each other. Mathematically, when you multiply a positive by a negative, you get a negative result. So within Coulomb's law, getting a negative force mathematically proves a physical attraction between the charges. If the result were positive, like say if both charges were negative, it would mathematically prove that they were repelling each other. The math flawlessly, perfectly mirrors the physical reality.
But the universe is rarely as simple as two neat little isolated charges hanging out alone. What happens in a chaotic, crowded room of point charges? That brings us to Section 4, Superposition, Dealing with Crowds.
I know the principle of superposition sounds intimidating, but it's actually a beautifully simple, logical recipe. Step 1. Just calculate the force due to each charge separately. You use Coulomb's law, exactly like we just practiced, for every single pair of charges in the area. You calculate them one by one, kind of mathematically isolating them from the rest of the group while you do it. Step 2. Add them all together as a vector sum to find the total net force. Now, because force is a vector quantity, meaning it pushes or pulls in a very specific direction, you can't just mash the raw numbers together. You have to use a vector sum to account for the spatial direction of each force. But the core concept, it remains elegantly simple. The total net force is just the sum of all those individual forces you calculated independently.
Okay, let's zoom out a bit, from the micro level right up to the macro level environment. Section 5, Visualizing the electric field.
So, what exactly is an electric field? Basically, it's the region around a charge where another charge will experience a force. Think of it like a giant, invisible web of influence radiating outward. If a charged particle wanders into that web, it instantly feels the effect. Mathematically, we calculate this using the formula E equals F divided by Q. The electric field, E, equals the force F divided by the test charge, Q. This equation tells us exactly how much force a single unit of charge would feel if it were sitting in that exact specific coordinate of space. And since we're dividing force by charge, our resulting units are newtons per coulomb, or N/C. The source also points out this can be expressed as volts per meter, or V/m.
Imagine how this field operates spatially in the real world. Right up close, near our primary point charge, the field has incredibly high strength. But as you move to a point much farther away, the strength drops off dramatically. Just like that physical force we calculated earlier with Coulomb's law, right? The electric field is super highly concentrated right at the source, but it dissipates significantly as you expand outward into the surrounding space. We kicked off this explainer that talking about the invisible architecture of the universe, and we've actually successfully decoded the math behind it. From individual charges, to calculating the exact forces, to mapping entire electric fields. So, I really want to leave you with this final question. If these electric fields truly dictate every single microscopic push and pull around us, what incredibly complex web of forces, literally calculating billions of tiny superpositions every millisecond, are interacting right now just to keep you sitting solidly in your chair instead of falling straight through the floor? The math might be totally invisible, but its spectacular results are constantly at work all around you. Keep wondering about those invisible fields, and I'll catch you in the next explainer.